Hi, hello. My name's Dr. Pete Edwards. I work at the University of Durham and I'm an astronomer here, and today we're going to talk about astronomy. So, let's start. We know there's gravity on the Earth, but is there gravity in space?
Okay, so here's my washcloth, like a magic trick, and now I'm going to get this soaking wet, and then we're going to see what'll happen when we wring it out. Meredith and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water's all over my hands, in fact. It wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jell-O on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
So from looking at the video of Chris, it's obvious that there is no gravity in space. But that's just not correct. You know, when you see the videos of guys floating around in the International Space Station, it's quite obvious that, you know, it's an obvious conclusion to draw that there is no gravity up there. But that's not in fact the case. And there's a thought experiment that Isaac Newton first came up with to sort of explain what's going on when something orbits the Earth. So in his experiment, Newton visualized a cannon on top of a very high mountain. The cannon's firing a cannonball, and if there are no forces of gravity or air resistance, the cannonball should just follow a straight line and fly away from the Earth. If gravitational forces act on the cannonball, it will follow a different path depending upon the speed of the cannonball. If the speed is low, it'll simply fall back to Earth, shown as A and B in this diagram. And that actually for the Earth, any velocity between 0 and 7,000 meters per second, the cannonball would eventually fall to the Earth. If the speed is just right though, the cannonball is falling towards the Earth, but it never actually gets there. You can think of the cannonball as falling towards the Earth, but the surface of the Earth moving away from the cannonball at the same rate. And that gives us what's called an orbit, and you can see that as C in the diagram. And for the Earth, that if you fired a cannonball at approximately a speed of about 7,300 meters per second, it would orbit the Earth. If the cannonball speed is higher, of course, than this orbital velocity, but not high enough to leave the Earth altogether, what we call the escape velocity, then the ball will continue revolving around the Earth along an elliptical orbit. The orbit wouldn't be circular, it would be an elliptical shape, like an egg shape. But the cannonball would still orbit around the Earth. And those speeds are roughly, 7,300 meters per second to about 10,000 meters per second. And of course, if the speed is very high, the cannonball would leave the Earth in a parabola and you'd never get it back. So there is gravity acting in space. When you're in the International Space Station, you're actually falling towards the Earth. Gravity is pulling everything down in the International Space Station, but they're all falling at the same rate. It's what we call free fall. So if you're inside the space station, everything around you is falling with you at the same speed towards the Earth, and so it would appear that there's no gravity acting. But we now know, of course, there is gravity acting, keeping the space station and its contents in orbit around the Earth. What about other planets? Is there gravity on the Moon, for example?
Whee! Boy, when you do this and you go down slope, that first step is a long one. I'm having... This is the best way for me to travel, uphill or downhill. What's that? Like this, two-legged hop. And on level ground, I can skip. I don't like that loping thing. Oh, the loping's the only way to go.
Checkpoint.
See, when I'm on level ground, I can skip. But this two-legged thing is great. Man, I can cover ground like a kangaroo.
So what's going on the Moon? You can see that there is gravity on the Moon, the astronauts bunny hopping around as they called it, but obviously the strength of gravity on the Moon is less. And we can explain that because the gravity of any object, the amount of gravity any object produces, depends upon the mass of that object. So on the Earth, the gravitational field strength, the downward force on a 1 kilogram mass is 10 newtons. And that's called the gravitational field strength, what we call little g actually. 10 newtons per kilogram. So the Moon has a smaller mass than the Earth, and so the pull of gravity by the Moon on any object is smaller. On the Moon, the gravitational field strength is only 1.6 newtons per kilogram. In other words, a 1 kilogram mass has a weight on the Moon of 1.6 newtons, whereas on the Earth it's 10 newtons. So you can see here the astronauts are hopping around in a lower strength field. The gravitational field strength of any object depends upon its mass. So a more massive object has a stronger gravitational field strength, a less massive object has a smaller one. So we talked about orbits. In space there are many things orbiting many other things. Planets like the Earth orbit the Sun. The Moon orbits the Earth, comets orbit the Sun too and move through the solar system. So the idea of orbits is an interesting one. We saw from the Newton's cannonball experiment that the force of gravity is actually the force that keeps the object moving in an orbit. If something has a force acting on it, Newton's second law tells us that it must be accelerating. But when you think about the orbit of a body, its speed isn't changing. It's still moving around the Sun. The Earth still moves around the Sun at the same speed. It doesn't change. So how can it be accelerating? The answer lies in the fact that acceleration is actually a change in the velocity of an object. Velocity is a vector quantity. So velocity is defined by the speed and the direction in which an object is moving. So even though when you're in orbit, your speed isn't changing, your velocity is changing because the direction in which your body is moving is changing. When you're in orbit, your speed doesn't change, but your velocity is changing. In other words, you are accelerating. If you change the radius of the orbit, the velocity of the body speeds up. And this is something that Kepler first thought about when he was looking at the motions of planets in our solar system a few hundred years ago. So here we have the ball in a stable orbit, and hopefully you'll see as I make the orbit radius smaller, the ball speeds up. So we've just talked about gravity in space and how things orbit other things, but now let's think about what's out there in space. What's doing the orbiting?